Welcome to the second Clay lecture by Mohammed Abouzaid, who today will speak about Bordism of orbifolds.
Thank you very much. I guess try and turn on light. Wait. So the first thing I want to start today with today is some motivation, because why would one think about Bordism of orbifolds? So I will give first some motivation even for why one would think about the kind of complex Bordism that I talked about yesterday. So this natural thing to do is to start with some, let's say, complex manifold. Let's call it M right now, with a vector bundle, with a holomorphic vector bundle. And one thing that happens is in very good situations, you can choose a holomorphic section and if you have an ample enough space of holomorphic sections, then if transversality holds, which does not always hold, then S inverse of 0, which is, I'll write as Z inside of M, this is going to be a smooth complex submanifold. Just essentially by just tracing through the definition. But this property of having enough holomorphic sections is, just does not work in general. If you take a general line bundle or vector bundle, it just won't be the case. I mean, this is the subject has terms for these things, very ampleness. But maybe you're interested in something a little bit, maybe you're trying to extract some invariant, something a little bit softer than complex submanifold. You can say, well, maybe I don't need to assume that this section S is holomorphic. Okay, so one of the advantages of the flexibility of differential topology over algebraic geometry. So in differential topology, we can always pick transversal sections. Generic. Here, transverse means so that the graph of the section is transverse to the 0 section. Something, some section like this. This is the 0 section. This is S. Okay. This point of intersection here is this hypersurface C. We can always do it, but then we lose, of course, something, which is that there's no reason anymore for the subset, for the submanifold that you get to be complex. It's only then Z, exactly what I talked about, right? Yeah, last time, stably almost complex. We just say stably complex. Okay. So this is probably part of the motivation for thinking about complex cobordism from the late 1950s. So I'm going to just say, especially see Herzebruck's work. Herzebruck's book. Okay, which is an expansion on this theme. Although he didn't use cobordism too heavily, but you can see that's how he was using methods from differential topology to study algebraic varieties. But so my motivation is in some sense it comes from an infinite dimensional version of this. Okay, so the same works, same strategy works if M and E are infinite dimensional. of appropriate type, okay, with satisfying some nicer properties. So the one way to say this is this could be a Banach manifold, complex Banach manifold, and this could be Banach bundle, and S could be a Fredholm section. Okay, where keywords are Banach and Fredholm. Okay. So where would such a thing appear? Well, such a thing would appear. We would encounter this. We encounter this in syntactic topology. Where you start with, let's say, I'm going to call it today X. Okay, so this is going to be a symplectic manifold. Now, I don't need you to know what a symplectic manifold is. So most importantly, from this, you can extract we can extract an almost complex manifold, which means that we can choose an endomorphism of the tangent space of X of J squared equals -1. So it's not quite this holomorphic thing, but every point in the tangent space you have something that looks like a complex structure, and it varies smoothly, but it doesn't vary holomorphically. And then again, just again some other black box, Gromov and Fleur, this and Fleur, they basically discovered in around 1985 to 1990, they discovered that somehow the way to extract interesting invariants of X is to study maps sigma to X, where this is a Riemann surface. And now we're essentially in this setting. So we want to study maps which are holomorphic, such that du composed with j equals j composed with du. What is this little j here? This is the complex structure on this Riemann surface itself. So I'm going to do this. And to see that this is the same setup over there, you just phrase this whole thing as you look at M being C infinity functions from sigma to X. Okay, so that's not quite a Banach manifold, but it's not really an issue here. Certainly, if you did CK, you would get a Banach manifold. And then this equation S, you rewrite it. So so rewrite equation du composed j equals j composed with du as a section of bundle on M with fiber, or basically 0-1 forms. So this, let me just not even do that. Yes.
Could you just tell us what that equation is?
Here?
No, below it, just below.
Oh, this is one that I wrote above. Du composed j equals j composed du. So this is the equation, this thing that says that this map, the differential of this map intertwines the complex structure on the Riemann surface with the complex structure on the target, which basically tells you this is a complex curve. Let me just not even write notation here. Okay, 1 forms on sigma valued in the pullback of the tangent space of M. So the X. Sorry. So what's happening here is, you would like to you would like to understand what it formulate holomorphicity as some conditions, and clearly you can just see du is a 1 form on sigma. It takes a vector and produces a number, but it doesn't really produce a number. It produces an element of the tangent space of X, and now you're just saying that you write this equation on it. Okay. So, okay, great. So if we could arrange for M to be literally a complex Banach manifold, and for J to be, and for this section S to be holomorphic, then we would be very happy, and we would deduce that the zero locus, which is this space of maps which satisfy this equation, is again complex, but that is not what happens in practice. In practice, what happens is exactly what I'm describing here. Okay, so you have the section is not quite holomorphic, but so therefore, the conclusion of this is that the space of such maps is stably almost complex. But so far, in fact, stably almost complex manifold. So here, sigma has been fixed. Now, the actual insight of Gromov and Fleur is that the space of such maps is not exactly what you want to study. What you want to study is the moduli space of maps, which means two things. One, you have to let the actual object of interest means the moduli space of maps. So one, we need to let sigma vary in moduli. So need to let sigma vary the modulus of sigma. This is the first thing. And then now you have to understand vary in what space, okay? And when I said here, I said, you should just think of it as a Riemann surface. It turns out that there is, when you actually try to set up this this moduli space, and if you only do this, if you only let the modulus of sigma itself vary, then you'll get something non-compact, because you'll encounter phenomenon like, I'm just going to draw some picture, some genus 2 curve like this. And then in modulus, you can imagine think in terms of hyperbolic geometry. It develops a very, very long neck. And then this neck can go to infinity. The length of this neck can go to infinity. And that's not a very desirable phenomenon for some space that we would like to think of as compact, because earlier some of this whole thing is about Bordism. Okay, so you need to let the modulus vary, and at the same time, you need to allow somehow certain things that are called stable maps, which are basically maps from nodal Riemann surfaces, where the mildest type of singularities with some control in what the map does, and in some special situations. Okay, so anyway, so these two things happen. If you try to actually build this, one of the immediate things that you realize is that if you have a Riemann surface with some non-trivial automorphisms, then you should not be looking at the zero locus. You should actually be looking at the zero locus modulo the automorphism. These two facts together imply that, well, actually, really just the first one, imply that, moreover, this forces one to mod out, to take quotient by the automorphisms of sigma. Okay. So once you do that, you're immediately in the land of orbifolds. Okay. So another way to say this is, if this did not occur, we would be very happy, and we would say that the output of this kind of Fleur theoretic or Gromov-Witten construction is some closed, maybe manifold. Okay, and this discussion tells you it's stably complex. And then whatever this black box work of Gromov and Fleur and whatever followed them, was done. It was done with some integer coefficients. You could try to do it now with Bordism coefficients and try to refine it. But this phenomenon tells you that this is absolutely not the case, and you have to construct some new Bordism theory. Okay, so now we discuss, so what is an orbifold? So if you notice here, I'm already suggesting that, it's not like I have a global group acting. I'm just saying, we're letting sigma vary, and then when sigma happens to have automorphism, we see some group acting, and then we have to take the quotient by that group. So that tells you that's essentially what an orbifold is. An orbifold is some kind of space. So informally, space which is locally modeled after Rn mod gamma, where gamma acts on Rn. This is a finite group. And the essential difficulty is to formalize this intuition. So, the short version basically is, well, gamma varies from point to point. So how are you going to describe, let's say, transition functions or something like this? And there are many, many ways around it. So there are many ways to formalize this. Ways to formalize this. But the thing that makes that's going to make it possible for me to give this lecture with a minimal amount of formalism technology is to point out a recent result of Pardon about 5 years ago, who showed that you can, at the cost of replacing finite groups by compact Lie groups, you can always present every orbifold as a quotient. Okay, so Pardon. I think 1919. So every orbifold compact orbifold is equivalent. Is, let me just say here, can be presented. Whatever, of course, to formulate this, you have to have one of the other notions. But what we're going to do, we're going to just bypass them and use this as our definition as a quotient. All right. Z. I'm going to write X G. Okay, and you should just take this as a definition. So what is this? This is a smooth compact manifold. This is a compact Lie group. And this action has finite stabilizers. With the property that for all x and x, okay, the subgroup of G such that Gx equals x is finite. This is a stabilized group. Yes?
Is that what you call a stack?
No. So one of the ways of formulating what an orbifold is would be as a stack with some properties. But I'm saying we don't need to know what that is. You just need to know what this is on this side. Smooth compact manifold with a compact Lie group action. That's something that's rather, I don't want to call it elementary, but certainly accessible to advanced undergraduates. So, this result was known under some additional assumptions earlier. So yeah, that's exactly what I'm trying not to do. So in fact, a better way to do so the way that I think about it is really just think of it as the data of this X and this G, and we will just work in the world of G manifolds, okay? And then at some point we will have to understand what equivalence relation should we impose to recover the notion of orbifold that we're interested in? So this is, you should think of this as notation, and maybe you should think of it as notation for x comma g comma, well, this action. So maybe you do it like this. G comma x. The pair consisting of this compactly group and this manifold acting on it. Okay. And such a thing determines an orbifold, but we don't need to worry about it because I'm about to say something further. So something where we'll just say everything can be rephrased just in this language. So that's the, for this lecture, this is what an orbifold is. A manifold, compactly grouped, and a G manifold, and so that the action is has finite isotropy. And the question is, that determines all the objects, and now we have to make sure we have the correct equivalence relation. Yes?
Is it related to the Borel?
No, don't do the Borel construction.
Okay, we want.
Yeah, I should not have used this notation, basically, is what this is telling me. Yes, yes. So really just think of it as the pair. Okay. So in fact, in Parton's theorem, he proves that you can choose G to be an orthogonal group. And this construction is related to the frame bundle construction. If you take a manifold and you look at the space of orthogonal, which is with the Riemannian metric, and you look at the space of orthogonal frames on it, then that has an action of the orthogonal group whose quotient is exactly the manifold itself. And this basically says you can do the same thing on orbifolds, except that this you don't necessarily, instead of taking the frame bundle of the tangent space, you can take some more complicated frames. You have to take some more complicated frames. Okay, so from this Lie theoretic perspective, when are two such presentations equivalent? Okay. So by that, I mean, I have this pair G0, X0, and I have another pair G1, X1. And again, without using the language of, one of these ways of formalizing the notion of an orbifold, how can we tell whether X0 and X1 are equivalent? Well, I will not give a complete answer, but there is a construction from which you can then deduce the other, deduce the other ones. And the construction is basically that you look for homomorphism from G0 to G1, okay, and the G equivariance map, and a G0 equivariance map from X0 to X1, okay, so that some properties hold. And then I will give it something general, and then I will explain kind of how to think about it. So that one induced map from X0 mod G0 to X1 mod G1. So here I mean it's just a map of topological spaces is homeomorphism. And two, there's three properties basically. The kernel of, or rather, maybe actually we don't have really to do this because it will follow from the other one. The induced map. Let me just give them the name F from G0, and here I'm going to say X to 1 f of X is an isomorphism. This says induced map on stabilizer groups. The essential thing that distinguishes orbifolds from manifolds is exactly this fact that locally you're not presented as Euclidean space, but rather Euclidean space with a group action. And so the origin gamma fixes this group gamma, clearly fixes the origin. This is a linear action. And so this basically says that the first part just says, if you were to take the quotient, every point here is equivalent to something in the image. And this second condition says, if you imagine that this double slash thing, which I don't want to define, somehow is remembering some data about how the group acts, but what this representation is, then that representation is the same. Okay? The group that stabilizes the group that stabilizes any point is the same on the left and the right. Okay. So again, not too complicated a definition, but let me just explain some special cases. So the first special case to have in mind is that if the action of G on X is free, then this quotient is just the usual quotient. So what I would say is that then G comma X is equivalent to just the trivial group and then X mod G. Okay. So if some of you know something about equivariant Bordism, in equivariant Bordism, there is, in computations of equivariant Bordism, roughly speaking, you have to think about the Bordism of the fixed point strata and separately about the Bordism of free manifolds. Okay, and in the orbifold theory, the Bordism of free manifolds just is collapsed, not to nothing, but to Bordism of their quotient. This is relevant because there were conjectures about unitary Bordism that like conjectures that it would be supported in even degrees, and those were optimistic conjectures, and those were recently shown to be false. But the way they were shown to be false is actually because the free part doesn't satisfy this. Okay, the free part, is very complicated. It involves the Bordism of BG, and that's very rich object. But if you think about orbifolds, then that's not something that you worry about. So this is the extreme case in which we're basically just taking a projection from G0 to the trivial group. Okay? The other thing you could do is that this is a special case. So another case to have in mind, important case is to have a group is to have an injective map. So given H to G, okay. You can associate to X comma H the X cross over H with G action, okay? And these two things are equivalent. And this is, you can say in some sense it's the reverse of this. It tells you that if most simple case A is a trivial group, it just tells you that if you take a manifold, then manifold cross G is equivalent to the manifold itself. Okay. Now, notice I used the word equivalent, not isomorphic. That's just some indication that clearly what I've described here is not invertible. Okay, so by that I mean if you have a homomorphism this way, satisfying these properties, it's pretty clear that in general you're not going to be able to find a homomorphism the other way and a map the other way satisfying these properties, and you can just see that in these examples. Okay, if if this G bundle is non-trivial, then you're not, this is twisted, then you're not going the other way will essentially involve something like this, and not every bundle, not every principal G bundle over space X is the trivial bundle. Okay, so that's just why I use the word equivalent instead of isomorphic. Now the advantage, one advantage of this definition is that now I really don't have to do much work to explain, for example, what it means to have an orbifold boundary. Okay, so an orbifold with boundary.
Have a global quotient which is not true.
Yeah. Then that's an interesting Bordism class, and we have to ask ourselves, what class is it? Yes, yes. But if it's, of course, the first non-trivial case to think about, you asked me, weighted projective space, that's very sophisticated. I can just take point and I equip it with the action of a finite group G. Okay, so this is an orbifold. It's the simplest orbifold other than a point in some sense, and it's these things are designed to tell you that this is not in any way obviously equivalent to a point. Boundary can be similarly presented as a G manifold with boundary. Okay, and the same thing with corners. Okay, and the only thing to say about corners is, this is what corners look like, and you want to make sure that in the normal direction the group acts trivially. So then that allows me to define a notion of orbifold Bordism group. We can define orbifold Bordism to be generated by pairs X comma G, satisfying this condition of finite isotropy. Again, X is compact, with relation. So as follows. So if I take X0 with G0, and I take X1 with G1, I would like to know when I have a Bordism between them. But then I have to remember there are these groups, and again, if I was a more sophisticated person, I would maybe have some language where I don't have to appeal to these groups, but I like simple concrete things, and that simple concrete things usually blow up to become complicated concrete things. So in the middle, I have some X01 and G01. And now what we want is for the boundary of X01 to decompose into two pieces. Let's call them boundary 0, X01, union boundary 1, X01. And this is just this picture that I drew last time, where I think of a cobordism as going from here to here. This is X0, this is X1, this is X01, except that now I have these groups floating around, and the groups should be allowed to change. Okay, so we have this thing. And how it should be allowed to change? Well, I just want an equivalence between this and boundary 0 of X01 with the group G01. It's there. And I should have an equivalence of the other one with boundary 1. Oops. boundary 0. It's horrible notation. X0, 1. And there's equivalence here. Okay, so before you just say this is a cobordism between that, and now you just say this is a cobordism between something which is equivalent to that and something which is equivalent to that. So, well, that's a notion. You have a set. You have an equivalence relation. Take the quotient. And now you have to do the usual game of trying to prove that that is, that you have an abelian group out of this. So let me warn you that actually this is trickier than usual. Now, usually this kind of thing is quite easy. The reason it's usually quite easy is because if I have a cobordism from this to this and then a further cobordism, let's just do it again. Let's say from this to the empty set, and then you can just glue them here. Okay, but in this world, you have to be careful because why would you glue them here? There's some group that's associated to this and some other group that's associated to this. So what group are you going to associate when you glue? Okay, you have to do some work. So it's non-trivial. So the quotient. I'm trying to say that another way to say this, that this is an equivalence relation rather than that you're taking the equivalence relation generated by this. If you take the equivalence generation generated by this, it's usually kind of nightmarish. This is an equivalence relation. And to be honest, this is the only, from my perspective, this is the only disadvantage of this concrete approach. Okay, this fact becomes non-trivial. If you take one of the more sophisticated definitions of an orbifold, this fact would be actually quite easy because an orbifold is a local structure. Okay, so it's a local structure, so it's very easy to patch together. This is some kind of global thing, and then it becomes difficult to see how you glue together. So what I will say is Hardin's proof that every orbifold can be presented like this goes through graphs of groups. So, I mean, here I would say, we're using it, but we don't necessarily speak about it explicitly because. Yes, yeah. So if you try to make some combinatorial theory, so what I'm trying to say is that my answer is something like thinking about graphs of groups is basically some way of trying to get rid of the compactly group floating here and thinking really more about what's happening in the quotient. Because there is a graph of groups relating, which is about the isotropy types from point to point. And the key issue is that there's issues of conjugacies along two cells, and you have to be careful about that. So there's two cells associated to conjugacies. But this kind of hides it entirely. Okay, so we are about halfway through, a little bit past that. What do we know about this group? Okay, so you may, again, if you are not an expert in the subject, you may ask, why am I even talking about this group? Again, remember, the motivation is something like you take some equation, which is, defined as some complex manifold maybe in the section, and then you maybe perturb the section in the world of differential geometry to produce a zero locus, which is smooth. And in this case, you have to take the quotient and orbifold. But you see, when you do that perturbation process, the diffeomorphism type of what you get is not fixed. Okay? It's only the Bordism class. So we want to understand that this output of the geometric machine that I alluded to here when I was talking about Fleur and Groff's work should be thought of not as one of these x0, x0, x's and g's, but rather such a thing up to this equivalence relation, right? Because you should be allowed to perturb. Well, I have good news, which is we know everything about this. It is 0. And the reason it's 0 is because I haven't talked about orientations. Okay. So I haven't quite used this yet, but it's pretty easy to see that you can take products of orbifolds, and it's pretty easy to see that the point, that the trivial group and the point is the unit multiplying. It doesn't change anything. But in the unoriented world, well, this is equivalent to Z mod 2. I want to write C2, but let me just write Z mod 2 with acting on Z mod 2. Okay, and that is the boundary of an orbifold, which is the interval with Z mod 2 action. So this bounds, therefore this bounds, therefore there's no invariant. Okay, so you have to say something interesting. In order to say something interesting, I have to be more honest, and I have to start talking about structures.
There is such a thing as ordinary equivariant Bordism.
There is such a thing, yes. Most people, basically, almost nothing is. I mean, you can compute a little bit, and what I would say is that the significant progress was done by Connor and Floyd in 1963, whatever, okay, in their book about cyclic groups. And then since then, I would say we have sporadic results, but not really the structure. And I indicated at some point here something about the difference between equivariant and orbifold Bordism is that free things do not contribute to orbifold Bordism. You just take the quotient. And free things, I assert, cause many of the issues in equivariant Bordism. So if you try to take that perspective, you have to be, you have to decide how much you want to throw out. The answer is you have to throw out a lot. Okay. Okay, so we need to talk about orientations. But again, the advantage of this formalism is that it's really very standard thing to do, to think about manifolds with some kind of equivariant structure, like, with an orientation, standard orientation, which is preserved by G. Okay, that's basically what you do. So for we just require that orientation. G action. Although it's actually better to have an orientation relative the Lie algebra. Okay, so I just let me not get into that. Okay, and similarly for U, this is the complex case. What you do is, so yesterday I gave some description of complex cobordism. I said, well, what it means to have a stable complex structure is that you have a manifold and a complex vector bundle, really pair of vector bundles and some isomorphism. So here you just say wire the complex bundles to be equivariant, to be G equivariant. Okay. And here it actually is really important, and add a copy of the Lie algebra. Okay, so let me just write it. What did I call it today? X. So what you want is, so last time I wrote Tx, direct sum E, this was minus, is isomorphic to Rn, direct sum plus sum. So this is the new factor. And the reason is because you are not looking. So this is a small difference from the, and the literature on equivariant cobordism can handle this. But basically, you're not looking for a stable complex structure on X. You're looking for a stable complex structure on the quotient. So if you want to test out that this is a reasonable condition, just check if X is like M times G, okay, then Tx will have a copy of the tangent space of M and a copy of the Lie algebra, and they will cancel out. And this is the same as M. Okay. if you know things about equivariant topology, you may be puzzled as to why I have a copy of Rn here because something else. Let me point out that this E plus and E minus are now equivariant G bundles. So inside of them, you can put any representation you want and hide. Okay. So again, you can instead put a representation here, but you can just slide it somewhere else. Okay. So that's the Bordism theory that we are actually interested in, and I'll give it a name. So for the next 15 minutes, we're going to be interested in the Bordism theories. The Bordism theory associated to unitary Bordism, unitary orbifold Bordism. So let's, oh my God, I'm going to use this upper script, spot here for just notating orbifold, denote the Bordism group of stably complex. Okay. Well, what do we know? Now we can ask, what do we know about it? Okay, it is not zero. Okay. So this group, I would say kind of, before anybody ever wrote it down, it was already known, kind of folklore. It has a map to Q. And what does it do? Well, Q, just rational numbers, it kills everything. By the way, this is as like last time, there is a number here, which is the dimension of the quotient. And this dimension is, of course, a non-negative number. And so this map lives just in degree 0. And the way this map is usually written is you just take point to the G action to 1 over the cardinality G. So the reason this is chosen is that, again, I just alluded to the fact that there is a product, and this is an obvious map to write down because this, if you take, this is a ring map, because if you take G1 and G2 and multiply them, then that will, then this will be a ring homomorphism with respect to that. It'll go 1 over G1, G2. Yes.
Let's see the complex structure.
No, nothing at all. Yeah, it doesn't see the complex structure. This map actually factors through the one for the orthogonal group. This one sees orientations. Okay. And now we can ask for more. So how can you go beyond this? So one thing that I want to point out is that actually it is not difficult to see that not only is there a map to Q, but there is a different map that goes to Z, which just sends 1 point comma G to 1. That will also be multiplicative. Okay. So in fact, there are tons and tons of homomorphisms from the degree 0 part of this orbifold cobordism ring to Q, to the integers. You can, for example, say, if the cardinality of this group is divisible by some prime P, I will send it to 0, and otherwise I will send it to 1. Okay, that is also a ring homomorphism. Now, to see that this is a ring homomorphism, you have to think a little bit about cobordism. You have to check that it is invariant under cobordism. So why is this map? Why are such maps well defined? Well, if I give you something, which is point mod G1, some orbifold, which looks like this. So these have stabilized at point 1 G1, and this has to point G2. Let me just do G0, 1. And I see some, more of them, and I see some cobordism like this. Okay. And this is point mod G1 comma 2, and this is point mod G1 comma 1. Well, if that happens, then this group and this group have to be isomorphic. Now, I drew this somehow just by taking the quotient, but in fact, this fact survives all these equivalence relations. So what I'm trying to say is that this is something well known from equivariant Bordism. So in equivariant Bordism from x01, so I'm going to keep the group fixed. G from x0 to x1. Again, we're going to keep the group fixed. Gives Bordism between fixed submanifolds for every group G, for every subgroup. And this is something very classical that, you know, Connor and Floyd, probably the starting point of Connor and Floyd's work. They considered the case of cyclic groups and then analyzed equivariant Bordism with respect to cyclic groups by decomposing it, as I was alluding to earlier, into Bordism of free things and Bordism of actual manifolds by looking at the stabilizer. Okay. So once you observe this, you realize that this is one of many, many, many different maps. Okay. What is their, you know, meaning? What are they good for? I don't have a very good answer. What I will simply say is that this is the class. This is the folklore map. There is another map that was, I mean, the other ones that I said are due to Fukai and Ono. And then, I mean, were first pointed out by Fukai and Ono, and then later there is work of Parker and by Chu. And they basically use, let me just say, they use the maps to Z. In fact, two different maps. So one of which says, if G is trivial, I send it to 1, and if G is non-trivial, I send it to 0. And the other one says, I send everything to 1. So all of those homomorphisms actually exist and have been used in the literature, usually not phrased using this language. But, you know, they have been noticed before. Okay, but now let's talk about something more interesting.
They use that map to prove what?
Oh, they use this map to prove that certain Floer-theoretic invariants can be lifted from Q to Z. But of course, they use it in some slightly more complicated setting. They don't use this language, but that's the first idea. The first idea is to break free of the expectation that you have to take that quotient that actually seems to have non-trivial content. And I just wanted to point out, as I said earlier, that there are many, many more maps. Just nobody has seen them, has seen a use for them. So the next thing that was known is, I want to say, observed by Kawasaki, but he pointed it out in the complex case, and then used by Giventhal. Okay. And then made more explicit in some work with McLean and Smith. And it says there is a map from Orbifold Bordism group. Now, I'm just not going to put this 0 here, the star, to K-theory of a point. So really, what is K-theory of a point? Well, I'll just say complex K-theory. So you can write this as Z inverse, and this is the degree 2 variable. Of course, it factors through the positive part. So this map is some. So I said Kawasaki first. This is some kind of holomorphic Euler characteristic. So the complex manifold, you can look at the ring of functions on it, holomorphic functions on it. Well, usually that doesn't have enough holomorphic functions on it. So instead, you take the Dobel resolution. That Dobel resolution is now a nice complex, and you take the Euler characteristic of that complex. This construction will send CP1 to 1, okay? Because, well, anyway, and then it will send the higher genus surfaces to basically half of their Euler characteristic, of their regular Euler characteristic. Okay, so that tells you this map is non-trivial, and what I'm alluding to here is that this map, in fact, extends the classical one, which is basically due to Hertz. So the fact that this map exists, and the fact that the map from this is usual complex cobordism. So that tells you that that tells you that these classes here are non-trivial. But you can then, but of course that's not what we were. That's in this work here. That's not what we were trying to do. We were not trying to compute this ring. We were trying to extract K-theoretic invariant from objects like this. So that's the motivation. So this implies you can extract K-theoretic invariant from complex orbifolds. Yeah, it tells you a lot, but it still doesn't compute it. Yes, tells you a lot. Okay. So the next thing that I want to say, I will say more vaguely. By the way, here I said holomorphic Euler characteristic. You have to figure out how you can. So that's of course for complex manifolds. You have to figure out how to construct a holomorphic Euler characteristic in the world of in the world of smooth manifold with stable complex structure. That's what Atiyah and Singer did with their in their index theory paper. That's papers. That's one of the main motivation is to formulate index theoretic construction that takes a complex manifold and produces a K-theory class. Okay. So in this paper with McLean and Smith, I'm not going to write their names again. We also construct similar maps. For more other K-theories. I don't want to say much more. Now, so that tells us a bunch of stuff about maps out of this, okay? But it doesn't tell us much about the structure, and I would advocate that the first question to ask about the actual structure is about this map here. So I'm going to state it as a conjecture, even though I expect this to come out paper not very long. Map from ordinary Bordism to orbifold Bordism splits as a map of cohomology. which means I don't mean something but coefficients. I mean that for every space X, there is, so this, I mean, I didn't describe it, don't have time for it, but this actually gives you of homology series. This is assigned to every space X some graded group, which is just orbifolds mapping to X, which is, now that we have this formulation with global quotients, it's very easy to say. And the splitting respects it. So why would we, so what would it mean for such a result to hold? Okay. I.e., we should be able to assign to every orbifold X comma G a manifold. That lifts it. And the strategy for proving this conjecture, so this is again in progress with Bai. Is to resolve singularities of X much. So I haven't been, this is partly why earlier I was saying, you know, if you have free manifold, if you have free action, and you think of that, you should think of that as manifold, so that's already the case. So you should just take the quotient, and if you encounter some singularity, e.g., say we have one point, one singular point, with stabilizer gamma. Okay, so you have Rn, and with this gamma action, and then you have some quotient. But now the whole assumptions that we put in, the assumptions on stable complex structures, would tell us that this representation is in fact a complex representation. Which means that this quotient, well, we can try to think about it. It's of course some orbifold, blah, blah, blah. But just what they would algebraic geometry, the core space of it, just the literal quotient, is an algebraic variety. Complex. You can just resolve it, and that will produce for you a manifold. And then you have to think about, why is this construction compatible with cobordisms? And that is because of something which in algebraic geometry is called functorial resolution of singularity. Reality of resolution of singularities. Implies that this survives cobordism. Yeah. That's it. Okay, so I will stop here. So in the afternoon, I will start by explaining how in Floer theory, we don't actually encounter orbifold itself. So this kind of result is not of rather limited use in symplectic topology and Floer theory, because you rarely encounter orbifolds. You can encounter a more complicated structure, which we call derived orbifolds. So what I will do is I will explain what derived orbifolds are. I will talk about the structure, and then I will again make some conjecture about how I expect the group, what I expect, some features of what I expect the group to look like. Okay, thank you.